Today's lecture is going to focus on key issue 1, 2, and part of 3. It's going to recap some of the concepts we already talked about yesterday. So geography is the study of Earth's surface, but it is far more than that. So geography is actually a bridge between science and social studies. Hence, that's why it's categorized as a social science. When we look at the difference between historians and geographers, for example, historians ask when and why, whereas geographers ask where and why. Historians organize material chronologically, while geographers organize material spatially. History and geography differ in one especially important way. A geographer can drive or fly to another place to study Earth's surface, but a historian can't travel to another time to study other eras firsthand. Human geography especially helps us make sense of how it impacts our day-to-day lives. One of the most important tools geographers use to study geography are maps. You'll see 3 maps down here below. We're going to look at those in more detail on the next few slides. A map is a 2-dimensional or flat-scale model of Earth's surface, so there are some shortcomings to that because it isn't quite the appropriate shape to show us what Earth's surface looks like, but it's the best way to get that on a flat surface. It can serve as both a reference tool as well as a communication tool. So when we think about it as a reference tool, typically we're looking at utilizing it for something. We want to get from one place to another. So think of a road map. Think of the maps that you see in your GPS when it's taking you from, let's say, your home to a restaurant. When we look at it as a communication tool, it means we're looking at it to gather some information maybe. Maybe we're looking at physical features. Maybe we're trying to gauge climate or vegetation, maybe economic activity, or maybe we're looking at population density. Contemporary cartographers today are assisted by computers and satellite imagery, so maps are pretty sophisticated. In the ancient world, many different models of how the world looked were proposed, as there was no way of knowing exactly what the Earth looked like or even if it was circular or flat. We're going to take a look at some of the earliest maps on record. Take a look at this map. This map dates back to 6200 BC. It depicts a town in present-day Turkey. Try your best to guess what this map is depicting. Archaeologists actually found this map on the wall of a house that was excavated during the 1960s. It depicts the eruption of Mount Hassan. And evidence indicates that the volcano actually erupted when this map was created. This next map is a world map by cartographer Ptolemy, and it's from 150 AD. The map shows the known world at the height of the Roman Empire, surrounding the Mediterranean Sea and Indian Ocean. Analyze this map. What do you see? What does it seem like land-wise they had a more understanding of? And what parts of the world did they not have much understanding of? What do the Americas look like? Are the Americas even on the map? The answer to that would be no. If you scroll across, you'll see the African continent, you'll see Europe, you'll see the Arabian Peninsula, and you'll see Asia. The next map you'll look at is a world map by Al-Idrisi from 1154. This map built on Ptolemy's map, the one that you saw before, but it had been neglected for nearly a millennium. So think of a millennium being between this map and the previous map you looked at. As you'll notice, there are far more details in this one, but still covering the same areas that were depicted in the previous map. This last map is by cartographer Ortelius from 1571, and this world map was one of the first maps to show considerable extent of the Western Hemisphere, as well as the Antarctic landmass. Take a look at how North America is depicted, South America, Africa, Europe, the Middle East, and Asia, and all of the islands in the Pacific, also known as Oceania and Southeast Asia. As I mentioned before, maps today are so much more sophisticated. When we think of maps today, we often think of GPS. Whenever you go on your phone to search up restaurants or stores, you're using your very own GPS. GPS stands for Global Positioning System, and this determines the precise position of something on Earth. And the way that GPS is configured is through satellites that are placed in specific orbits, tracking stations to monitor these satellites and receivers to pinpoint locations. GPS can be found not just in electronic devices, but also in airplanes and cars. Who would have thought that you all would be carrying your own GPS device in your pockets, in your backpacks, on your wrists? It's really quite amazing. How are maps used to convey information? Well, we talked about this yesterday, and some of you mentioned the last time that you used maps, you used them for things like trying to find a restaurant or navigating a bike trail or trying to complete a map quiz. But as I also mentioned yesterday, maps can be really powerful because it's a visual representation of information. And so that information can be used to lead individuals to have a perception of what it is the producer of that map may want to convey as a message. We discussed this regarding the map of the Middle East that was included in yesterday's lecture. We're now going to start talking about interpreting maps. And so there are a few different factors that geographers use to interpret maps: map scale, projection, and latitude and longitude. Yesterday, we spent quite a bit of time talking about map scale. So again, when we're talking about a large scale, we're talking about more detail. And when we're talking about a small scale, we're talking about showing a larger landmass, but with less detail. So less detail with a small scale and more detail with a large scale. We're also going to be talking about projection, and that's looking at maps, this two-dimensional depiction of Earth's surface on a flat surface. And lastly, we'll talk about latitude and longitude and how that helps us make sense of absolute location. Since we talked quite a bit about map scale yesterday, we're going to get right into projection today. So when we look at projection, we're looking at Earth's surface being transferred to a flat map. Now, when that happens, however, you're going to lose some authenticity to what Earth actually looks like. And so you're going to see distortion on several levels. You're going to see distortion when it comes to shape, when it comes to distance, when it comes to relative size, and when it comes to direction of locations. One activity that can help you understand how transferring Earth's surface to a flat depiction can create distortions is if you were to take an orange, for example, and you were to draw a map on that orange in relation to a globe, and then you were to peel that orange in a perfect peel and then try to lay that flat on a table. Imagine what that would look like and how different that would look in comparison to the maps that you're used to looking at every day. When we look at the world depicted on a flat surface, we notice that the area on a map might look longer or shorter in comparison to what it actually looks like in real life. So that's what we mean when we say that shape could be distorted. We also can see distance distorted. So for example, the distance between 2 points on a map could be increased or decreased in order to make that more visually appealing to us and for us to be able to comprehend the land masses that exist. Relative size is also something that is going to look different on a map. Some areas might actually look a lot bigger on the map. And so when you're comparing continents, for example, or you're comparing certain land masses, one may look considerably larger than the other. And then you also have direction. So when we talk about direction, what could be distorted is the direction between two places, looking like it could appear twisted, for example. There are many different types of maps, and depending on the map, you may find that in order to minimize the distortion in one category, they end up increasing the distortion in another category. Let's talk about some of the maps that are depicted here. This first one, for example, is the Mercator projection. It's got several advantages. If you notice, shape is distorted very little, direction is consistent, and the map is rectangular. Its greatest disadvantage, however, is the relative size is grossly distorted toward the poles, making high latitude places look much larger than they actually are. So take a look at Greenland and take a look at the African continent. Seems very distorted as Greenland is not anywhere close to being the size of the African continent. The next map is the Goody-Homolycene projection. The primary benefit of this type of projection is that the relative sizes of the landmasses on the map are the same as in reality. The projection minimizes distortion in the shapes of most landmasses. Areas to the north and south poles, such as Greenland and Australia, become more distorted. But since they're sparsely inhabited, distorting their shapes usually isn't considered that important. This last map is the Robinson projection. It's useful for displaying information across the oceans. Its major disadvantage is that by allocating space to the oceans, the land areas are much smaller than on interrupted maps of the same size. We're going to watch this video on projection together after this lecture. Take a quick look at what the Mercator projection does to the size of Greenland in comparison to Africa. This is what it looks like on the Mercator projection, and this is what it actually is. Pretty astonishing, right? Next thing we're going to talk about is latitude and longitude. Now, we talked about this yesterday, so I'm only going to cover it briefly. You've got your meridian lines and your parallels, and when these lines intersect, they help us pinpoint exact locations, also known as absolute locations on Earth's surface. The equator is the parallel line at 0 degrees, and the prime meridian is the meridian line at 0 degrees. Meridian lines help us make sense of the world's time zones. So the prime meridian is the main time of the world, and it runs through Greenwich, England. If you were to cross the international date time, which for the most part is at 180 degrees longitude, you'd cross this line and you'd move your clock back or forward 24 hours. Have any of you ever done this? So when you think of the meridian lines, every 15th degree represents a time zone. So there are 360 lines divided by 15 equals for 24 time zones. This is what Earth looks like depicting latitude and longitude lines. Right after this lecture, we're going to be watching two videos, one on map distortion and the other one on time zones. So right after that, we'll have our discussion. This is where it ends, and I'm going to go ahead and stop the video here.